everyone. This is Dr. Sandeep Kumar, Assistant Professor, Ramjas College, Delhi University. So, in the last lecture, we were discussing about the pyridine compound. So, in pyridine compound, we have discussed that pyridine compound can show three kind of reaction. Reaction due to its basic nature, the second reaction electrophilic substitution reaction, and the third reaction nucleophilic substitution reaction. Then we also discussed that the oxidation at the carbon atom of pyridine is not feasible. In fact, the oxidation at nitrogen atom of pyridine can be carried out. So that's why pyridine undergo substitution reaction in place of addition reaction. Then we started with the basic nature of pyridine molecule, and in the basic nature we discussed two type of reaction. The first reaction, the reaction of pyridine with hydrochloric acid that produced pyridinium chloride as the salt, and the second reaction, reaction with methyl iodide that produced N-methyl pyridinium iodide that is also a salt. So these two reactions confirm that pyridine is basic in nature. So the basicity of pyridine can also be compared with pyrrole. So we know that pyrrole is a very weak base, whereas pyridine has a basicity comparable to that of aniline. That means pyridine is as basic as aniline molecule, and their basicity is respectively like pKb value is 8.7 for pyridine and 9.4 for aniline, that are very close. But these both compounds, pyrrole and pyridine, are less basic than aliphatic tertiary amine. The pKb value of tertiary amines is around 4. So basically the basic nature of these heterocyclic compound is due to the presence of this lone pair of electron on the nitrogen atom, and the availability of this lone pair of electron for the protonation will decide the basic nature or their relative basic nature of these compounds. So what is happening in pyrrole? The nitrogen's lone pair is delocalized into the pi electron system of the ring and making it unavailable for the protonation. As a result, pyrrole is extremely very weak base. What is happening? This lone pair of electron is a part of aromatic sextet, means there are 2 pi electrons of this double bond, 2 pi electrons of this double bond, 4 pi electrons, and these this lone pair of electron also participate in the aromaticity of pyrrole molecule. So total there are 6 pi electrons, and that's why this lone pair is not available for the basic nature of pyrrole. But in case of pyridine, the lone pair reside in an sp2 hybrid orbital and does not participate in the delocalization into the pi electron system of the ring. Hence, it is more readily available for the protonation, and further pyridine is more basic than pyrrole. So in case of pyridine, the nature of this lone pair is just opposite that was in case of pyrrole. In case of pyridine, this lone pair is not participating in the aromaticity. In fact, it is available for the protonation, and this is the reason for the more basic nature of pyridine than pyrrole. Now the second type of reaction on pyridine is electrophilic substitution reaction. So the electrophilic substitution reaction on pyridine takes place at position 3, and why the position 3 is more preferred than position 2 and 4, this can be understood by taking the example of the mechanism for the electrophilic substitution reaction. So, the mechanism of electrophilic substitution reaction can be understood like the reaction take place in 3 steps. In the first step, there will be generation of electrophile, that means we have generated the electrophile, and in the second step there will be attack on this electrophile, and after the attack there will be formation of resonance stabilized carbocation intermediate. And you can see there are 3 different intermediates which are resonance stabilized, and this step is also the slowest step of the mechanism, and that is why this is the rate determining step for the electrophilic substitution reaction on pyridine. So, after the attack on the electrophile, now there will be removal of proton by the nucleophile in the third step, and we will have 3 substituted pyridine as the final product. So, the reason for the orientation why the position 3 is more preferred than position 2 and 4 can be understood by taking the assumption of step 2, that is the attack on electrophile. So, when we assume that the pyridine will attack on the electrophile at second position, then we will get these 3 different intermediate, and these 3 different intermediates are also resonance stabilized. Similarly, we can assume the attack on the fourth position of pyridine, and in this case also we will have 3 different resonance stabilized intermediate. But the problem is that in these 2 kind of attack, when the attack was at position 2, then there was formation of an intermediate, that is intermediate number 4, and when the attack was at position 4, then there was formation of an intermediate, that was intermediate number 8. So, you can see in these 2 intermediate there is positive charge on the electronegative atom, and this positive charge on this electronegative atom will make these intermediates highly unstable. But when the attack was at position 3, then there was no intermediate where the positive charge was on the nitrogen atom. That is why the position 3 is more preferred for the electrophilic substitution reaction rather than position 2 and position 4 of the pyridine molecule. Now, we will discuss the reactivity of pyridine for electrophilic substitution reaction. So, you can see the reactivity of pyridine is less as compared to benzene molecule for the electrophilic substitution reaction. The reason for this reactivity can be understood like in case of pyridine, the 6 pi electron density is contributed by 5 carbon atoms and 1 nitrogen atom. But in case of benzene, the 6 pi electron density is contributed by 6 carbon atoms only. So, what is happening? Due to more electronegativity of nitrogen atom than carbon, it pulls the delocalized pi electron density towards itself, and this result in a reduced electron density on the carbon atom of the pyridine ring compared to those in benzene. So, that is why pyridine is less reactive than benzene for the electrophilic substitution reaction. In fact, this nitrogen atom deactivates the ring in a manner similar to how a nitro group deactivates nitrobenzene towards the electrophilic substitution reaction. Further, the second reason for the low reactivity of pyridine for electrophilic substitution reaction can be understood that most of the electrophilic substitution reaction like nitration, sulfonation, halogenation, Friedel-Crafts alkylation, Friedel-Crafts acylation, they take place in the presence of acidic condition. So either we use protonated acid or we use Lewis acid. So when we use acid in the electrophilic substitution reaction, the nitrogen of pyridine ring, due to the basic nature of pyridine, will get protonated, and in this way the pyridine ring become more electron deficient, because of nitrogen atom will withdraw the electron density from the remaining carbon more efficiently. So that's why pyridine undergo or we can say pyridine is less reactive than benzene for the electrophilic substitution reaction. So we can see some kind of examples from the electrophilic substitution reaction. The first is nitration of pyridine. So nitration of pyridine by using nitric acid and sulfuric acid at 300 degrees Celsius can be carried out, but the problem is that in the synthesis we get only 15% yield. So the yield can be improved by using potassium nitrate in place of nitric acid. So when we do reaction of pyridine with potassium nitrate by using sulfuric acid at 573 Kelvin, then there will be formation of 3-nitropyridine in around 70% yield. Then the sulfonation of pyridine is also feasible by using sulfuric acid and mercury salt at around 250 degrees Celsius. So when we do reaction of pyridine with sulfuric acid at 250 degrees Celsius in the presence of mercury salt, then there will be formation of pyridine 3-sulfonic acid. And when we increase the temperature at 360 degrees Celsius, then this pyridine 3-sulfonic acid will be converted into pyridine 4-sulfonic acid. Further, the next electrophilic substitution reaction on pyridine is halogenation. So pyridine undergo halogenation with elemental chlorine or bromine at 300 degrees Celsius to produce 3-halopyridine and 3,5-dihalopyridine as the mixture of products. So you can see the bromination of pyridine at 300 degrees Celsius is producing mixture of product, that is 3-bromopyridine and 3,5-dibromopyridine. So if we want the production of single product, then we have to use this condition. So for the bromination, if we have bromine in acidic medium like sulfuric acid, then this will produce a single product, that is 3-bromopyridine. And for the chlorination, if we are using chlorine in presence of aluminum chloride, then there will be formation of 3-chloropyridine as the single product. Now the Friedel-Crafts alkylation and acylation are not feasible on pyridine molecule because these reactions require Lewis acid or acidic condition. So when we use Lewis acid or acidic condition, then the nitrogen of pyridine ring will get protonated, or it can form a stable complex with the Lewis acid, and that's why it deactivates the ring for the electrophilic attack, and hence the Friedel-Crafts alkylation and acylation reaction on pyridine is not feasible. Now we are going to discuss the third kind of reaction on pyridine molecule, that is nucleophilic substitution reaction. So in nucleophilic substitution reaction, we will discuss two kind of observation. The first observation is that pyridine is more reactive than benzene for the nucleophilic substitution reaction. This is just opposite with the case that was in electrophilic substitution reaction. In electrophilic substitution reaction, what we discussed that benzene was more reactive than pyridine, but in case of nucleophilic substitution reaction, what we are going to discuss that pyridine is more reactive than benzene. And the second observation is that for the nucleophilic substitution reaction, position 2 and position 4 are more preferred than position 3. So let's start with the first observation, that is reactivity of pyridine for the nucleophilic substitution reaction. And what we found that pyridine is more reactive than benzene. The more reactivity of pyridine can be understood like we know that nitrogen atom is more electronegative than carbon atom, and hence nitrogen pulls the electron density towards itself and makes the carbon of pyridine ring electron deficient, and that's why due to electron deficiency on these carbon atom will make the nucleophilic attack feasible. That's why pyridine is more reactive than benzene. Now the second observation is that the nucleophilic substitution reaction in pyridine takes place at position 2 and 4 rather than position 3. So this can be understood like pyridine undergo nucleophilic substitution reaction at 2 and 4 position because of electron withdrawing effect of the ring nitrogen atom. The electron density is reduced more significantly at the position 2 and position 4 than at the position 3 of the pyridine ring. As you can see, in these three intermediates there is positive charge on the second position and fourth position. So you can see that there is no positive charge at the third position of pyridine. That's why the nucleophile will prefer to attack at the position 2 and position 4. Now among position 2 and position 4, the nucleophilic substitution reaction preferred at the position 2 of the pyridine ring, because in this case the contributing resonance structure, that is 1 and 3, which involve minimum charge separation, are more stable than structure 2 where the charge are more widely separated. So that's why among position 2 and 4, the preferred position for the nucleophilic substitution reaction is position 2. So this is the first example for the nucleophilic substitution reaction on pyridine molecule. So the reaction is also named as Chichi-Babin reaction. So in this reaction there will be introduction of amine group at second position of pyridine, and this amination is carried out by heating pyridine with sodamide, that is NaNH2, in presence of toluene as the solvent, followed by aqueous workup. So this is pyridine molecule on treatment with sodamide in presence of toluene at 373 Kelvin, followed by aqueous workup, will undergo the formation of 2-aminopyridine. The formation of 2-aminopyridine can be understood by the mechanism. So the reaction takes place in two steps. In the first step, the amide ion attack the second position of pyridine ring, that leads to the formation of a carbanion intermediate, and this intermediate can be represented as a resonance hybrid of 3 contributing structure. These structure 1, 2 and 3, and this is the slow step of the reaction, and that's why it will serve as the rate determining step of the reaction. So after step 1, where we got resonance stabilized carbon ion intermediate, in the second step these from the resonance stabilized carbon ion eliminates hydride ion that result in the formation of the final substitution product, and this step is rapid and therefore does not participate in the overall reaction rate. So you can see that this carbon ion will eliminate the hydride from the intermediate and will produce 2-aminopyridine as the final product. So we can see some kind of nucleophilic substitution reaction on pyridine. So the first reaction is reaction of pyridine with potassium hydroxide at 573 Kelvin followed by acidic workup. It will produce 2-hydroxypyridine, or we can say 2-pyridol. It is resonance stabilized, or we can say it is tautomerized into 2-pyridone as well. The second reaction, that is nucleophilic substitution reaction, is reaction with phenyl lithium at 383 Kelvin. So when we do reaction with phenyl lithium, then there will be formation of 2-phenylpyridine as the final product with the elimination of lithium hydride. The third reaction is reaction of pyridine with butyl lithium at 383 Kelvin, and from here we can synthesize 2 substituted butyl pyridine as the final product. So now we are going to discuss the nucleophilic substitution reaction in pyridine derivative. So what kind of pyridine derivative? Those which have substitution at second and fourth position. So you can see these two examples, that is 2-chloropyridine and 4-chloropyridine. When these derivatives are treated with a nucleophile like secondary amine or ammonia at 200 degrees Celsius, then there will be nucleophilic substitution reaction at their respective position. So when 2-chloropyridine is reacted with any nucleophile, it will produce 2 substituted pyridine derivative, and when 4-chloropyridine is reacted with nucleophile, that is ammonia, then it will produce 4-aminopyridine as the final product. So the mechanism for this nucleophilic substitution reaction in case of 2 and 4 substituted pyridine can be understood by taking the example of reaction of 2-bromopyridine with ammonia molecule. So the reaction take place in 2 steps. In the first step, the reaction begins with the nucleophilic attack attacking the carbon atom bearing the leaving group. So this kind of attack where the leaving group is present is also known as ipso attack, and after this attack there will be formation of anionic intermediate. Then in the second step, from this anionic intermediate there will be elimination of bromide ion, and we will get 2-aminopyridine as the final product. So in these 2 steps, what we found that in the first step there was addition of nucleophile, and in the second step there is elimination of the leaving group, and that's why such kind of mechanism is also known as addition elimination mechanism. So these are some examples where nucleophilic substitution reaction can be carried out at second and fourth substituted pyridine derivative. So in the first example we have 2-chloropyridine. On reaction with secondary amine, it will produce 2 substituted pyridine derivative. If there are 2 substitution at second and fourth position, that is 2,4-dichloropyridine, on reaction with thiol nucleophile, it will produce second and fourth substituted thiol derivative of pyridine. Then the reaction of 2-chloropyridine can also be carried out by using ammonia at 200 degrees Celsius. Then it produced 2-aminopyridine as the final product. Then the reaction of 4-chloropyridine with ammonia will produce 4-aminopyridine as the final product. So now we are going to discuss the nucleophilic substitution reaction in 3 substituted pyridine derivative. So in contrast, 3-halopyridine generally do not undergo bimolecular nucleophilic substitution reactions because the resulting anionic intermediate lacks the stabilization by resonance structure as that was in the case of 2 and 4 substituted pyridine molecule. But still the reaction at 3-halopyridine is feasible by the nucleophilic attack, but in this case the mechanism will be different. So in this case a benzene like mechanism will take place, where in the first step there will be elimination of the halo group from the 3-halopyridine, and we will have pyridine as the intermediate. And in this intermediate, that is pyridine, now there are 2 electrophilic site, that is position number 3 and position number 4. So in these 2 electrophilic site, by the attack of nucleophile, we will have a mixture of product, that is 4 substituted pyridine, that is 4-aminopyridine, and 3 substituted pyridine, that is 3-aminopyridine. And since the reaction is taking place in 2 steps, in the first step there is elimination of the halogen, and in the second step there is addition of the nucleophile. That's why this kind of mechanism is also known as elimination addition mechanism. So now we will discuss the reduction of pyridine molecule. So the reduction of pyridine molecule is possible in both way. Means we can do the reduction in complete way, or we can do the reduction in partial way. So for that we can use different kind of reducing reagent. So when we use nickel on hydrogenation at 473 Kelvin, or we can use sodium in ethanol, then pyridine undergo complete reduction and will produce piperidine as the final product. If we use burst condition, that is sodium in liquid ammonia in presence of ethanol, then there will be kind of partial reduction will take place, and we will have 1,4-dihydropyridine as the final product. The third kind of reduction can be carried out of pyridine by using lithium aluminum hydride by in presence of ether as the solvent, and followed by acidic workup that produce 1,2-dihydropyridine as the final product. So this is also a kind of partial reduction of pyridine. The fourth kind of reduction of pyridine can be carried out by using hydrogen iodide in presence of red phosphorus. So when we use this condition at 573 Kelvin, then there will be formation of N-pentane and with the elimination of ammonia. So basically in this reaction, the pyridine ring is cleaved into an open chain organic molecule, that is N-pentane, with the elimination of ammonia. Now, as we discussed that the oxidation of pyridine is possible, but the oxidation can be carried out at the nitrogen atom, but it is not possible at the carbon atom. So, when we do oxidation of pyridine by using perbenzoic acid, then there will be formation of pyridine N oxide and benzoic acid. So, that means the oxidation at the nitrogen atom is taking place by using oxidizing agent. So, this was all about the pyridine molecule. In the next lecture, we will discuss about the indole and related compound. So, thank you very much.